Today I'm going to be going over the relativity worksheet from last week. So I copied all the questions over from the worksheet into just the general note document. So I'm going to be filling things in here just so I have as much space as I need. So first question here we have electrons in a circuit and a 9-volt battery moving at 1,778,000 meters per second. Find the Lorentz factor for these electrons. Okay, so we're solving for gamma for this speed. So we have 1 over 251 minus, so v squared, that's going to be 1.80 squared divided by 300 million squared. Do that down there. All right. So, let's get out the calculator. 1,778,123 squared is, boy, what is that in, that's the 12. Okay, so we have, so 3 point, I'll do 161. And then speed of light squared is 9 times 10 to the 16. So, oh wait, so that's divided by that. 3.51. Say 4. Yeah. And to the negative 5? Negative 5. Okay, so then we have 1 minus that. It's this here, so that's 9. I'll do 6, 5. Okay, then we squared it. 4 nines. And then 82437. I'll do that. 2437. Is that it? 82437. Yeah, okay. So then 1 over that, and our answer is 4 zeros. 17563. There's our gamma. That. Okay. So, calculate the observed mass of an electron at this speed. Okay, so the observed mass, and that's the rest mass. So, this is going to be solving for m prime. So that's m times gamma. So 9.11 times 10 to the negative 31 times 1.1234, 17563. 9.11016, basically. So, yeah, it is a little bit bigger. You know, not a lot bigger, but a little bit bigger. All right, next up, what do we have? We have the originally calculated above speed of finding equal to kinetic energy. Okay, using the new observed mass, calculate the kinetic energy needed to move the electrons to the above speed. Okay, so now we're saying, all right, we have now what the, let's find kinetic energy, which remember kinetic energy is 1/2 mv squared. But now we're actually going to, instead of m, we're going to use m prime. So we're going to use the mass that we just got. So we have 1/2 times 9.11016 times 10 to the negative 31 times the speed, which we at the beginning, which was the 1.783, and that's squared. Okay. So let's see. What's our mass? Let's divide this by 2. 4.55508. Okay, so then we're going to multiply this now by that speed squared, so times 1,778,3 squared. Okay, that's that, right, that's the speed squared, so I'll write this in. Where was it? Yeah, it was that there. 3.161 and to the 12, not 21. Okay. All right. So then, what do we get? We get 1.43999 times 10 to the. Why am I? Oh, because I didn't have. Okay, that's why. Yeah, I forgot that I had this the negative 31. So hold on. Times 10 the, like that should not be that. Okay, yeah, that there we go. Okay, so 1.43999. Okay. So there's our answer. So D, a 9-volt battery gives electrons 1.44 to 10 to 18 joules. This is enough energy to electrically proceed. So basically, is this energy enough to get the kinetic energy we need? And yes, it is. Right, 1.44 negative 18, 1.43999, and that's why I specifically didn't round it because yeah, it is less than 1.44. So, yes. So the point of this is to say that you have something that's moving again, like over a million meters per second, and so there is a relativistic effect here, but it's so small that like functionally it's everything still works, right? It's not like by moving an electron at through a circuit your battery stops working because of relativity, right? So yeah, that's kind of the idea behind this there. Okay, now we're moving on to number 2. So Voyager 1 is moving at 17,260 meters per second, is a rest mass of 721.9 kilograms, and has been traveling since September 5th, 1977. What is the Lorentz factor? Okay, so again, solving for gamma. And so the speed here, we have 17 to 60 squared divided by 300 million squared. Okay, so we have 17 to 60 squared is 2.9790.97. B to the 7th? No, 8th. Yeah, 8th. Okay. Alright, this is going to be a small number. Because we're dividing this by 16 divided by that. Oh boy, okay. 1, so that's 1, 2, 3, 4, 5, 6, 7, 8. That. Oh boy. So that was the wrong one. That one. Okay. So 1 over square root of. So now 1 minus this. That's a lot of 9s. 1, 2, 3, 4, 5, 6, 7, 8 9s, and then 6, 6, 9. Okay. 1, 2, 3, 4, 5, 6, 7, 8. 6, 6, 9. So square root this. And oh boy, still 8 9s. and then 8345. 345. Let's space it out again. So our final answer is 1 over this. Okay, so that's 8 zeros, 1655. All right, there is our Lorentz factor for Voyager 1. Okay. What is Voyager 1's observed mass? So again, we're solving just like for up there, we're now solving for m prime. So the mass of Voyager 1 is 721.9 kilograms times 2, 3, 4, 5, 6, 7, 8, 1655. Okay, so times 721.9. All right, so that's 721.9. How many zeros? 1, 2, 4 zeros. And then I'll round to 1, 2 kilograms. So that is, how much is that? Okay, so that's kilograms. That's hectograms. That'd be grams. And that would be grams. Okay, so this is, it's a little bit more than 1 milligram heavier than it actually is. Basically, is what it appears to be. Which, I don't know. It looks like it has like an extra little bit of dust on it. I don't know. Okay, so Voyager 1's perspective, how long has it been traveling out far the future? Okay, so this one, though, you have to be careful. Because again, remember that the prime numbers are the numbers that we see outside of the moving object. Okay, so the question is asking, from Voyager 1's perspective, in other words, from the perspective of the thing that's moving, how long has it been traveling? Okay, so we have seen it traveling since September 5th, 1977, so we have seen it traveling for a certain amount of time. So in other words, the time that we are seeing is actually t prime, and this asks you to solve for t. Okay, so this formula is still true, but we're solving for t this time. So t prime, it's how much time has it been since storage space. Oh, I don't right now. I know my storage space is low. Let's see. So okay, so what we can do is how many days since September? I think the first option on there was like the beginning of quarantine. That's actually kind of funny. Okay, September 5th, 1977. If you do this, it'll just spit out a number for you there. So 15,595 days. Well, I guess when you fill out this worksheet last week, it would have been a few less days, but whatever. It's not going to make much of a difference. So the time that we have seen, and you can keep this in days, that's fine, is 15 minus 5 equals the gamma, or equals t times the gamma, which is, where is it? 1.12345678165. So we're actually going to be dividing. So t equals 15 minus 5 divided by that there. Okay. Whoops. Okay. Just get back to what I had here. Okay. So, and then flip it. Okay, so that's our answer. Yes. So let's do that. That many days. So then the question for how much is it time travel into the future, that is the difference in time. So the difference in time between these 2 days. So t prime minus t, so 15,595 minus 15,594.999974 is, yeah. Okay. That's 0.1234 2581. So in other words, it's Voyager 1 has actually time traveled into the future by that much of a day. Which, if you're wondering, we can convert this into like, so how many hours is this? Well, that'd be times 24. So like nothing. Okay, how many minutes is this? So that's times 60. Okay, that's still kind of not really anything. So how many seconds is this? Times 60 again. Yeah, so it's 2.23 seconds. So Voyager 1 has technically time traveled into the future by 2.23 seconds after it's been traveling for like 43 years. So, yeah. But there you go. Now you know. We did it. Congratulations. Okay, anyway. Alright, number 3. Assume proton has been traveling as the light. Okay, so this is the same kind of situation as the previous question, because this is saying, hey, we have seen the universe age this much, which means we will have seen the proton move at this much. So, when I was asking to find out how far is it time traveled in the future, the time that we're actually solving for first is t, not t prime. So it's going to be t equals t prime divided by gamma. Now, gamma, I'm going to cheat and just use the fact that we found it's at 10% the speed of light. We found that earlier. Where is it? That's homework. Where are you? Where's the thing I made? Here we go. 10% speed of light. Okay, 1.005. From 0.1c. So 10% the speed of light. Okay. So, we therefore have, what's our time? So our time, our t prime, is 13.8 billion. So that's 13.8 to billion. That's billion divided by 1.005 equals. Let me actually just quickly double check this to make sure my numbers are right, because it would be point. There it is. Okay, so that's the more accurate number for gamma, but whatever. I'm just being nitpicky here. Okay, so divided 13. And we want to inverse. Yes, okay. Okay, so that's actually a noticeable difference. Okay, I'm gonna copy this full number actually, just to be precise. 0.0, so that's actually pretty nice. Alright, so that is our time. So how much is it time traveled? Well, that's going to be, again, t prime minus t. It's the difference in the times. So we have 13, 8, but that's too many zeros. Minus 13, 730, 826, 632. Right, so we have equals 69, 173, 367, or 368, 368 rounds. Years. So that's our answer. So, again, a proton moving at 10% the speed of light, it has time traveled over 69 million years into the future, which, again, that's more than, dinosaurs went extinct about 66 million years ago. So, yeah, that's a pretty big change in time. Granted, again, this is moving at 10% the speed of light for this long, which is, less than, well, it's about this percent of a difference in time. So that's like about 0.5% of difference. So, yeah, it's not very much compared to 13.8 billion years, but, compared to us, that's a lot of time. So that's something. All right, here's the ridiculous one. So, energy consumption of the Earth is about 6 times 10 to the 20 joules in a year. Let's say this energy used to send a 100 kilogram person forward in time. Because math increases during relativity, kinetic energy needed to move an object at relative speed equals that equation. Okay, so this person has factor B. So the point of this is to say that here I have all this energy, and it's going into this kinetic energy, specifically this relativistic kinetic energy. So what this question is saying is this here, and I'm solving for gamma. So, because I have that this number equals 6 times 10 to the 20. That's my kinetic energy. So, what other numbers do I have here? I have, so I have gamma minus 1 times 100, that's the mass I have, times c squared, okay, so that's that, and that equals 6 times 10 to the 20. Okay, so, well, the easiest thing so far would just be divided by 100, which would turn this into, and also c squared is 9 times 10 to the 16. So divided by 100, this becomes 6 times 10 to the 18. So, gamma minus 1, nope, I forgot the, equals, actually I don't need the gamma if I'm dividing this over. I don't need the parentheses. Okay, so 6 times, so I'd have 6 times 10 to the 18 divided by 9 times 10 to the 16, which would actually, wouldn't it just be like 6, didn't this just be like 66.6 repeating? Anyway, okay. 3, 6, 9, 12, 15, 18, 6, 7, 9, 12. Yeah, 66.6 repeating. Okay. So gamma minus 1 equals 66.6 repeating. So, therefore, gamma equals 67.6 repeating. So, there you go. That's your gamma. Again, this is very ridiculous. So how fast would this person be going? Now that we have the gamma, we have the Lorentz factor, we can go backwards to solve for the velocity. Okay, so first thing we got to do is, again, it's 1 over this equals this. So, hold on, wait, plus 1. Okay, so then we got to 1 over that. Get that there. So we get that the square root of 1 minus v squared over c squared equals, boy, not the greatest number in the world. I'll just do this. Is that like a, that's a repeating fraction. It's a really gross one. I don't know. Anyway, I'll do that. Okay. So then you square both sides. So we get 1 minus v squared over c squared equals this squared. Which is, oh boy. Okay, this is a good enough number to round to. So that's 2. Okay, that's 3 zeros and then 2183. So 1 minus this ends up being that v squared over c squared equals, I'll round it to that, is that. So which therefore means you have to square root this at this point. Oh boy. No, I'm gonna round it here, actually. I'm gonna go pretty precise for this one. Because at this point, you're getting to very precise, since the numbers are, as you can see, very close to the speed of light, it does actually matter. Oh, this should be a 6. Small differences can actually make a big difference here. So this is that times c. So now let's multiply this by, oops. Right. So here is our speed. That many meters per second. So yeah, you can see that's very fast. And again, if you were to actually, we're working on this based off of the fact that c is 300 million. It's actually 299,800 whatever, 299,800 something thousand. So this number actually is bigger than like the exact speed of light, but again, we're working with like proportionality here with this, so it's fine. Don't worry about that too much. So what would this person's mass be observed to be from outside of the time machine? Okay, so this is now, since we're outside of the thing that's moving, we are solving for m prime. So we're just going to use 100 times the gamma, which the gamma we got was here. Let me hold that actually. Okay. So for answer, therefore, we get instead of 100. So wait, how should I do this? I'll do. Wait, no, I wanted 200 divided by 3, right? Yeah, and then plus 1. Okay, so that's the right thing. Okay, so we want that. Well, times 100 would just be 600. Oh, 6,000. Okay, so this also would be 6,766 points. Okay. So yeah, that is our mass. You can see it definitely increased a good amount. So if the time machine was turned on New Year's Day 2020 and the person was in it for 1 year, what year would it be when he stepped out of the time machine? Okay, so since now again we're talking about where the person was in it for 1 year, that means while they are inside the time machine, they are inside the thing that is moving, they experience 1 year. What does everything else experience? So we are solving for t prime. And if they're in it for 1 year, that means, well, 67 years. Okay, so now the question though was, what year would it be? Okay, and so if this amount of time has passed, right, then, well, if you started in 2020, right, it's that many years. But the question is, what year is it? And in a sense, as I said that, like, we specifically started on New Year's Day, well, since we're starting at the very beginning of the year, sure, there's an extra 2/3 of a year that's gone by, but we're still going to be in the year of 2087. So, yeah, because if I, for example, if I said we started in like, I don't know, July, let's say July, well, I don't know, 4th or whatever, then because of this extra 2/3 of a year, it will have rolled over to early 2088, right? But since I said we started in New Year's Day, it is going to be in the year 2087. So, yeah, if you want to use all the energy produced in the world, we could send someone in time to into the future into 2087. We have the technically we have the capability of doing this. Not the engineering for it like at all, and also by using all the energy consumption of the world, you will have like completely crippled civilization. So congratulations, you destroyed everything just to time travel. But like, eh, do you? I guess. There you go. There's the answers to all this fun stuff. Yeah. Again, this stuff it's weird because like mathematically this is not that difficult. There's just some things that are. I mean, the numbers are not great. And the Lorentz formula is a little annoying to work with. Um, but the main challenge here is just kind of conceptually understanding what to do and what numbers are used when. And for example, when are you solving for t? When are you solving for t prime? Right, and that's kind of the whole challenge with that. Which, yeah, I don't really know what else to say about it. Except that it can be tricky. So, yeah. Um, okay. Well, I guess that's that. So let me. Okay, so tomorrow, Tuesday, we're gonna have one more lesson of new content, and that's gonna be sort of a timeline of the universe from the beginning to the end. Um, well, the presumptive end. There's actually a couple different ideas about what will happen. Um, but at the same time, though, there is one where basically the ideas are given certain factors, this will happen, this will happen, or this will happen, and the thing is, we know what the factors are right now. There's a possibility that the factors could change, in which case, therefore, the prediction changes. But based on how things are going right now, we do know what will happen. Um, well, again, of course, assuming there's not some new information that we randomly know about. Um, anyway, so that's going to be Tuesday. Um, Wednesday, I'm gonna be reviewing um, units 5 and 6. So atomic stuff and waves, and then Thursday I'll be reviewing units 7 and 8, so electricity and then the astronomy stuff. And then Friday, I'm gonna give you the final. The final is going to be again same, very similar in format and structure to the electricity test, but it will be 60 points, and um, it'll be the same length of the first semester final. So 60 points, 8 questions in total, um, 2 questions per unit. Okay, so that's the same kind of idea with that. I'll show you the formula sheet that you'll have access to as well, because I'm going to add on astronomy stuff to that. So yeah, that's and for the final you will have. Again, I'll give it to you on Friday, so you'll have Friday. You'll have the that long weekend, right? Monday is the holiday. I mean, it doesn't really matter at this point, but you know. And then the all of next week, you'll have time to work on the final as well. So yeah. Next week, Tuesday. Uh, if you remember how there was like a long Kahoot at the end of first semester, I'm gonna be doing the same kind of thing next week, Tuesday. So that'll be there. Um, let's see. Anything else I want to point out? I don't think so. Uh, yeah, and that's basically the end of the year. This year's been interesting. Very interesting. Well, that's it for that, so goodbye.